Hello there. We're going to discuss about the graphical representation of work. Actually, we will try to get the idea how from a graph of force and displacement, we can get the idea how much work is being done. So let's see this. This is the graph and you can see over here in the y-axis, we have taken the measurement of force applied and in the x-axis, we have taken the displacement produced. So suppose there's a box. We can take a box and when 1 Newton force is applied on the box, then it is moving to a displacement of 10 meter. So you can see when 1 Newton is force is applied, then 10 meter it is producing. So it will come some over here. Okay. Then when 2 Newton force is applied on the same box, then it is producing 20 meter distance. So somewhat it will come over here. Okay, 2 Newton and then 20, and we will go like this. It will keep on coming like this, like this, and like this. So you'll see when we have taken the force and displacement, here we are taking displacement this side and we are taking force this side. So the graph is coming over here. And in this case, you might have noticed that the displacement is being produced in this exactly in the same direction where the force is applied. So in this case, work gonna be F dot S cos 0 degree because force and displacement both in the same direction. So angle between them will be 0. So theta gonna be 0 over here. Now understand this. In this case, in this scenario, work will be exactly multiple of force and displacement. Okay. Now we're going to do what? We're going to shade the area under the graph. What is the area under the graph? This is the area under the graph. So we exactly going to shade like this. And this is the area under the displacement and force graph. Okay. Let's get this idea. What is this area is signifying over here? Now, if you'll see this under this area, basically one side displacement is coming. This side is displacement is coming. We can say S, and this side you'll see force is coming. We can say F. So you can see this shaded area is actually making a triangle. I've shaded it very badly, but somewhat it is looking like a triangle. So we can give the name A, B, and C. Now we know the area of a triangle is equals to half into base. The base will be AC and height will be CB. Now when you're putting the value, AC is representing what? Displacement. So I'll put S and CB will represent force. I'll write F. So it could be written as half SF or half Fs, which is actually the expression of force. So we can equate the equation number 1 and 2. You might be thinking, no, here is half. But in the case of dimension, we can remove this half. It is just a magnitude it is representing, not actually the quantity it is representing. You're getting this? Like there is a force, Newton, if I'm just talking about that there is a force of 2 Newton or there is a force of 1 Newton, but both of them is representing force. So instead of doing like this, we can write work is equals to half Fs. Or we can say it is the area under force and displacement graph. Area under force and displacement graph. So we can conclude one thing from here is whenever we have to find out the work from any graph, we can just write down area under force and displacement graph. And this is very crucial because many times the question comes from this section also. So you have to be very equipped with this idea. Let's take the another example. I'm just drawing the another graph over here. We will get the idea very clear. Not just this time this type of graph comes, but sometime different graph comes also. So let's see this one. We are having a graph, another graph over here, where we will take the force. I'm going to take the force this side. This time I'll take the force this side. We can take any side. So just I'm making you to understand one thing, that we can take with our convenience, or sometime in the examination you will find it is in the different places. Okay, and we are taking this displacement this side. So suppose there is a constant force of 20 Newton. This is the 5 and 10 and then 20 Newton applied. Okay, and it is this constant force is keep on producing displacement 10, 20, 30, 40, 50, and keep on displacing. So the graph gonna be like this. When the force is constant, only displacement is increasing. So graph going to be like this. Okay, now what we're gonna do in this case, we have to shade over here. Okay, so I'm going to shade this. Okay, so this is exactly the graph coming under the uh, area, actually coming under the displacement and force. Okay, this time I've shaded a little better than previous one. Okay, so we're going to understand this. Let's take this one. Okay, now see this. Here the total force will be 20 Newton, or you can give the name like this one will be A, and this is B, this is C, and this is D. Okay, now see this one. So what will be the work? Suppose we applied this 20 Newton force on a body and it produce a kind of displacement. We can give like 10, 20, 30, 40, 50, and this will be 60. It produced 60-meter displacement from the initial position from A to B. So you can see over here in the same way, whenever there is a force and displacement, both are in the same direction. So we can represent with the easily with the graph. So here again, Fs cos 0 will be, and then work will be Fs. Now here you can see what will be the area. Area. Area will be, you can see it's looking like a square, but we will consider a rectangle for some time. Okay, now area will be AB into BC, we can say. Now AB is representing force and BC is representing displacement. So we can write, give the equation 1 over here. You can give equation 1, this is equation 1, another area. We can give F into S, or we can write AB is equals to AC. So BC. This will be the equation number 2. Now we can equate both equations. So we can say work is equals to area under, what kind of area it is? Under force and displacement graph. Hope you understood this. And we will solve some similar question related to this one. Now we are having two graphs over here. You can see in one graph we have got the magnitude. So let's solve this one first, and then we will go back to this graph. Okay. So this is the question that you're seeing here. You can see Newton it is representing. That means it is talking about the force, and you can see this is the meter it is representing. That means it's talking about the displacement. Now the question is you have to find out the work done, total work done from this graph. So you can see actually graph is this. This one is the actual graph. Okay, one line it will be. Now what will be the area under this graph? This is the entire area will be under this graph. Okay, now we have to find this area. You can see this is a trapezium, and we know the area of trapezium. Better to give the name A, B, C, D. So area of trapezium we can say A, B, C, D. We know it is half of the sum of the parallel side. Sum of the, what is the sum of parallel side? These two lines are the parallel, we can see. So we can write AB plus BC multiply the distance between them, perpendicular distance between them. So this is AB is the perpendicular distance. So I'm writing AB. Now put the value half. AD is over here. You can see the graph, it is coming over like more over like 4. So give 4. And BC is over here is almost 8. So give 8. AB. AB is from 30 to 60. That means 30 to 60 it will be 30. Okay, now you can add this up. It will be approximately 12. Half. You can multiply 30. Cut down this. You can cut down 6. Now 6 multiplied it is coming 30 into 6 will be 180. Now 180 is what? We know one side is in the meter, so I'll write meter. Another side is in the Newton, so I'll Newton. Now remember, area we were writing like meter square, but here area actually representing by the different quantities. So one is the Newton, another one is the meter, and which is the unit of work as well. We're going to discuss in this video later. So this is the unit of the work, you can understand. So this is the area we have got, and this is the value of work done. Okay, this is the total work done we have got, which is 180 Newton meter, or sometimes we say joule. Okay, instead of writing Newton meter, we can say joule. In the same way, we can solve this one also, but you can see it is not shaded in the case. So we have to shade now. Let's pick up some brush and start shading this. But here the quantity is not given. So let's suppose we will take some quantities. Okay, we can take over here, we will take force this side, and this side we will take displacement. Suppose the displacement is of 20 and the force is of 8 Newton. So we can find out what will be the area. Area will be 8 into 20. This will be 8 into 20. This is 160. Now force we can take Newton, or we can take different unit. I'm taking dyne, and I'm taking this centimeter. So it will be dyne centimeter. Okay. So this is the another question that we have solved by taking some assumptions. So this is the area, and what will be the work done? So work done will be whatever the total area we find out. This will be 160 dyne centimeter. So this is the unit, another unit in a CGS system of the work. Instead of saying dyne, we say erg. Remember this. So we have understood how we can find out the work done by just understanding the area. Remember, whenever we are saying that work done, we have to find. So we can, and graph is given. So we just need to see the area under the graph and shade the area and get the value of the work done. So let's talk about the unit of work. We're going to discuss about the unit of work. Unit is very important because it gives you the exact measurement in which scale we are measuring. Okay, now we have understood one thing, that work is nothing but it is the product of force and displacement when the angle is 0 we are taking. So we can write Fs, or you can write cos theta, no problem. Okay, and you can see over here work unit is Newton, and this displacement mostly we can take meter, which is an SI system or MKS system we can say. So SI system in Newton it will be there, and instead of writing Newton meter we can say joule. We can say joule. So 1 joule we will write 1 Newton 1 meter. Sometime in the board examination question comes to define 1 joule. So how we can define 1 joule? So we will say when a body having any mass, it's not necessary to mention, when a body is subjected a force of 1 Newton produced a displacement of 1 meter, then we can say the work done is 1 joule. Now, I'm just repeating it, understand? Work done of 1 joule could be said when a force of 1 Newton is applied on a body and it is producing a displacement of 1 meter. Okay. Now, another unit which is in the CGS system. What is the another unit? Instead of writing work in Fs, I'll just directly write this. Instead of writing force unit Newton in the CGS system, the unit of force is dyne. Okay, and the unit of displacement is centimeter. So instead of saying dyne centimeter, we can say erg. 1 erg is dyne centimeter. Hope you understood this. So how we can define 1 erg? So we can say when 1 dyne of force applied on a body producing a displacement of 1 centimeter, so we can say work done is 1 erg. Now we have to find out the relation between joule and erg. So we will start writing from the joule. 1 joule is equals to 1 Newton 1 meter. Now this is the CGS system, so we have to convert this SI system into CGS. So we know 1 meter is equals to 100 centimeter and 1 Newton is equals to 10 to the power 5 dyne. Okay. So instead of writing this, we can write 50 and including 2 zeros, so this will be 7 zeros. Okay, and we will write dyne centimeter equals to 1 joule, and we know dyne centimeter is equals to erg, so we can say 10 to the power 7 erg. So we have understood, or we came to the conclusion that 1 joule is always equals to 10 to the power 7 erg. Hope you'll remember this and you like my video. If you like my video, please do subscribe it and comment if you want some clarification. I would love to discuss your clarifications and queries. Thank you so much.